afternoon, everyone, and thank you for joining us. We're glad to have so many of you with us, not only from Ontario, but across Canada and the United States. My name is James Smith, and I'm the Manager of Member and Technical Services for the Ontario Good Roads Association. It's my pleasure to welcome you to this webinar, Accelerated Bridge Construction, brought to you by Acro Limited. Over the next hour, our two distinguished presenters, Betul Oliver, Business Development Manager, Acro Limited, and Dr. Michael Barker, Professor, University of Wyoming, will discuss how modular and off-site construction of steel bridges are delivering benefits and efficiencies in terms of reliability, durability, and cost effectiveness to infrastructure projects that are not achievable using traditional methods or solutions, specifically concrete. Some general housekeeping before we begin. 1, all attendees have been muted for the webinar. 2, you may ask questions. It's strongly encouraged. To do this, use the question and answer pod functionality within Zoom. Gordon Scott, Director of Sales and Operations for Acro Limited, is working behind the scenes to respond to these. Third, the webinar is being recorded. It will be made available on OGR's website and YouTube page for future reference. Now, please help me welcome our first presenter, Betul.
Thank you, Dr. Smith, for the kind introduction. Thank you, OGRA, for hosting this webinar and making it possible for me to reach all of you today. Thank you to all the participants for joining today. Hopefully, you'll find this to be interesting and informative. I'm going to start off by giving a little bit of background about Acro to provide some context behind who we are and what we do. I'm going to then explore some common challenges faced by bridge engineers when specifying a bridge. My guest speaker today, whom I will introduce shortly, will discuss the findings of his analyses, which system is ultimately better, steel or concrete. Afterwards, I'm going to take the floor again and discuss the Acro 700 XS modular bridge system and examine its use in accelerated bridge construction. And finally, we'll look at different bridge applications and explore the use of modular steel panel bridges and how they can resolve various bridge infrastructure challenges. So Acro was established in 1951. We're not new kids on the block, we've been around. We're a world leader in design, engineering, and manufacture of prefabricated modular steel bridges. We have offices across the USA, Canada, and the United Kingdom. We acquired Maybe Bridge just last year in 2019. So we do have offices in the UK now. We do have local staging yard in St. George, Ontario, and our Canadian head office is in Toronto. We also have an office in Vancouver and in Montreal, Quebec. It's a proprietary steel technology derived essentially from the Bailey Bridge system. The Bailey Bridge system was developed by Sir Donald Bailey back in the time of World War II, and the Army used this to help sort of fight the war, and they would quickly assemble these and go across. So our system is derived from it, but it is not to be compared with the Bailey system. It is called the Acro system. It's a panel bridge system, and it has been it has advanced over the years, and I will discuss that a little bit later. And our company does have over 200 employees worldwide. So what we do permanent bridges. Often we're known, when you hear the term panel bridges, we're known for temporary or emergency bridges, international emergency bridges. But we have our fair share of permanent bridges, especially here in Ontario and in Canada. So we do permanent bridges, we do temporary bridges, as well as military, emergency, and development programs. The facility, we have our fabrication manufacturing facility, Milton Steel Company, in Milton, Pennsylvania, 21 acres of facility. It has a capacity for 25,000 tons of bridging per year. We have 95 team members operating over 3 shifts, and we have all sorts of high-tech equipment, 8 robot cells, 26 robots, CNC plasma cutting machines and drills. You might be thinking to yourself, I signed up to hear about accelerated bridge construction, not to hear all about Acro, but I tell you who we are and our capabilities, really to sort of convey to you that we are an established and sophisticated world-class organization. We have 70 years of experience under our belts, and we know the challenges that bridge engineers like yourselves face. So some of these challenges, and I'm sure there are more, but I've listed some of the key challenges, namely failing or inadequate structures. Structures designed before the 1980s generally have a design life of 40 to 50 years. So, here we are in 2020, many bridges are now nearing the end of life. Also, another challenge is limited budgets. That's always a challenge. Municipal tax revenues alone are not often sufficient to build and maintain rural municipal infrastructure. Federal, provincial funding and assistance programs are often not sufficient and typically are too inflexible. So that's definitely a challenge, and it's always a consideration when considering what type of bridge system to use to make sure that it fits within budgets. In terms of taxpayer demands and pressures, nobody likes gridlocks. Taxpayers don't want lengthy and inconvenient detours. Also, detours that divert local traffic to another bridge or have them traveling through the town can not only have a negative effect on local residents, but can result in expedited deterioration of those detour roads and alternate bridges as well. That volume of traffic still needs to go somewhere. And taxpayers do have some say. They have some pull, I guess, in varying degrees with different cities, municipalities, counties, and townships. Other challenges, new infrastructure and maintenance of infrastructure of bridges is very expensive. Building and maintaining transportation infrastructure is the single biggest expense for most rural municipalities. Bridges are the most expensive cost element within that inventory. So that's definitely a challenge. Design costs are high. When you're looking to install a new bridge or to retrofit an existing bridge, you get a consulting firm involved, and consulting fees are high, and typically they fall anywhere between 10 to 20% of a bridge cost. So that's a consideration as well. And if you can find a system that is pre-engineered, that might save some money in the long run. Environmental regulatory requirements. So this is a big one. There are significant provincial and federal regulatory requirements when working near water infrastructure projects. The requirement for bridge piers can thus have significant environmental study costs and lengthy approval times. So ideally, you want to try to eliminate piers where you can, and select a system that will allow you to do so. Changing infrastructure needs over time. Cities are always growing, and oftentimes there is a need to sort of change your bridge structure, maybe to widen it, maybe to accommodate 2 lanes of traffic versus 1. Yet bridges are the least flexible infrastructure component for accommodation of unpredictable functionality changes, traditional bridges. So that's definitely a challenge that bridge engineers face. With all these challenges and considerations, how do you know what type of bridge system to select for any given project? What system costs less and performs better in the long run? Well, here's somebody who will tell you which system is better. He's carried out a large-scale analysis on bridge structures and will summarize his findings for you today. Dr. Michael Barker received his Bachelor of Science and Master of Science in Civil Engineering Technology from Purdue University and his PhD from the University of Minnesota. He's a professor of civil and architectural engineering at the University of Wyoming and a Bridge Technology Center representative to the Short Span Steel Bridge Alliance. His primary research pertains to steel bridges, experimental testing, bridge design specifications, bridge field testing, high performance steel, and reliability analyses of structures. We're very privileged to have Dr. Barker's distinguished presence here with us today. And without further delay, I will pass the mic on to Dr. Barker.
Thank you, Betul. And welcome everybody. Good afternoon. So I'm going to talk about life cycle costs of typical steel and concrete girder bridges. as the director of education for the Short Span Steel Bridge Alliance, I talk to a lot of counties and a lot of consultants and a lot of state DOTs. And one of the most common questions they have is, yeah, we understand about first costs, but what about life cycle costs? Which are the best bridges for life cycle costs? So that's what we're gonna deal with today. Whoops, it did work, but it worked twice. So what I'm going to cover is a historical life cycle cost of steel and concrete bridge girders. And the reason it's historical, because if you talk to the steel industry or you talk to the concrete industry and you ask them, what about life cycle costs? They give you this anecdotal evidence and they make up their numbers and they say, hey, look, we're better than concrete. Or the concrete people say, hey, look, we're better than steel. So as part of my work, what I did was I actually looked at historical life cycle costs. What really happened? And I'm looking at historical life service, or what I call performance and maintenance, and then agency life cycle costs, the true agency costs for a bridge. And it's on a database of bridges in Pennsylvania. Now, since I only have 15 minutes here, I have to make this real quick. So this is really a teaser for you. And if you're interested in this, you go to the shortspansteelbridges.org website and you can see the full report. So we're just going to play a little bit with it. So life cycle cost data, what we need is the whole life history of a bunch of bridges. We need a comprehensive inventory of bridges if we're going to do some comparisons, which means we need initial costs and the date built and all the maintenance costs and the date performed on that bridge. And then we need to know how long that bridge lasts, or the end of service date. Well, the bridges in the Pennsylvania inventory are still in service, so I had to come up with an end of life model, which we'll discuss very briefly. But the second part of this was I really wanted to look at typical bridge structures and modern typical bridge structures. So we're talking about precast I-beams, boxes where the boxes are adjacent to each other, boxes where the boxes are spread with a deck between them, steel rolled shape and welded plate girder bridges. And since I'm looking at modern typical bridges, pre-stressing, precasting, all that kind of stuff came on the market in about 1960. And that was also the time that steel bridges really became better at detailing and fabrication and erection and those type of things. So I looked at bridges built between 1960, and then I cut it off at 2010. Then, of course, I needed to know everything that happened to every one of those bridges for it to be in the database. So PennDOT has over 25,000 bridges in their database. Of those, over 6,500 are of those 5 types of bridges. And then when I studied those over 6,500, I came up with a list of steel rolled beam, steel plate girder, box adjacent, box spread, and pre-stressed I-beam bridges. And here we had a little over 1,700 bridges that met all the criteria, which means I had the information on everything that's happened to those bridges, which represents a little over a quarter of the potential 6,500 bridges, which is a pretty good representation. So now that bridge life model, again, remember, I'm going through this fast because I only have 15 minutes, but all this is really well explained in the report. And there are hour-long videos on that website to where if you are interested, you can go and watch those. So I had to come up with a bridge life model. When was that bridge going to be replaced? And I based it on deterioration rates, historical deterioration rates for all 6,500 potential bridges, where if I assume the bridge was a superstructure condition rating in the US, that's what we use, of a 9 when it was first built, which means it was a perfect bridge, then given that I looked at these bridges in 2014, I can calculate a deterioration rate. Then, if I assume that bridge is going to be replaced when it reaches a 3, then I can calculate the remaining life. And then the bridge life is just how old is it now plus the remaining life. But an important part of this, and our first results from this study, is this table here, where it's looking at average deterioration rates, or the condition rating loss per year. And so here's a results table. And at the bottom right, you see two of the bridge types, steel rolled bridges and precast box spread bridges. So when we see these results tables, you're going to see the best and the second best performing in whatever we're looking at. So for instance, steel rolled beams is 7.1% of a condition rating loss per year. And the worst is not that much worse than that. And that's why that statement on the bottom left is there, that all are similar with none way out of balance. And you're going to see that on several of my tables. And then I'm going to deal with that bottom left statement at the end of my little presentation here. So now we're just going to zip through this. Looking at an example, a life cycle cost of a bridge. This is a precast spread box beam bridge. It was built in 1969. It's got 3 spans, and yes, it's in feet, not metric for you Canucks, but you guys understand feet better than we understand meters, and so you'll be able to understand that. But the important part is in 2014, it had a superstructure condition rating of 5. And these type of bridges had an 8% deterioration rate per year. So I can predict the remaining life is 25 years. From 1969 to 2014, that gives me another 45 years. So I am predicting that this bridge lasts 70 years. Now we deal with the costs. Of course, the costs are based on US dollars, again, making fun of the difference between the US and Canada. But anyways, it was built in 1969 for $141,000. Now I divide it by the deck area so I can compare bridges to bridges, but that's $1969. And then in 88, there was some maintenance, and in 09 and 13. And I took every bridge in the database and I said, okay, we're going to pretend they are going to be built in 2014. And so I use construction cost indices to take care of the inflation to bring all those up. So here are the costs in constant 2014 dollars. Now I lay out that timeline. Here is one life cycle for that bridge. It's built in year 0. In year 19, 40, and 44, there are maintenance events, and then it lasts 70 years. Now we're going to find a present value cost for this thing using a discount rate of 2.3%. And we find a present value cost, which is what we do in life cycle costing, of $154.50 per square foot. Which kind of means, if we had that in the bank when we wanted to build this bridge, we could build it, that money would sit there, and we could pay for those 3 maintenance events. And when we are done, the money is gone. But this causes a problem because this bridge lasts 70 years. And I can't compare that to a bridge that only lasts 40 years because the outcomes are not the same. And so what we do is we use perpetual present value cost, or what's more commonly thought of as capitalized costs, that assumes that we replace that bridge with an equivalent bridge forever. And when we determine the capitalized cost, that comes out to about $194 per square foot, which again means if we had that today, we could build the bridge now, pay for one cycle, and at the end of that cycle, we'd have that money there again to be able to do that forever. Now with capitalized costs, we can compare bridges directly. So all of those 1,700 bridges I put into Excel sheets, 3 of them for each type of bridge, where, I had a file for general information where it was location, year built, spans, length, area, geometry, materials, and that kind of thing. And then the second file was department and external contractor maintenance performed with costs and dates. And then the third one is really the results, where we look at initial costs and life cycle costs and capitalized costs, and even present value of future maintenance costs. And I did that for all 5 types of bridges, and then I went to the report writing part. Now, like I said, shortspansteelbridges.org is a great website. You can find this report on there that involves everything that's shown here on the left. There's also an additional report there that just looks at or extends what I did with the original report for galvanizing steel. And that's an interesting report. It's quite a bit shorter. But on the left here is what the report involves. We looked at present value costs and capitalized costs and all that kind of stuff for different variables. Now, I'm only going to look at the light blue today because of limited time. And so here we go. So here is bridge life. Which type of bridge lasts the longest? And if we look at the average bridge life over here on the right side, down below it, I say steel rolled beam has the longest expected life, and then precast box, where those boxes are spread, has second at over 81 years, and the low is 74 years. That's still not a big difference. You know, we're only talking about 7 years difference here. There is a difference, but only 7 years. So there's my statement on the bottom left that say, again, all are similar with none way out of balance. And now we come to the money part. Okay, so this table shows the results for the whole database. Okay, all of the bridges in the database. And so you see the number of bridges that were in the database, the perpetual present value costs or the capitalized costs. And we see that for all of the bridges, for all of the database, the precast I-beam has the lowest perpetual cost. Steel rolled beam is second. But again, none of them are way out of balance there. So there's that statement on the bottom left. All are similar with none way out of balance. But this table also shows the initial costs and the present value of future costs. The average length, the average number of spans, the average year built, those are pretty consistent, and the average life again. And this is one of the problems, you know, it's hard to compare directly precast I-beam bridges or adjacent boxes, which are usually simple span bridges, to bridges, you know, plate girder bridges that, you know, over here it says average number of spans over 4. And then the average lengths, you know, the average length of a plate girder bridge is 406 feet. Even for the rolled beams, 166. And so, you know, just this is good to look at, but we need to narrow that down a little bit. And since I'm part of the Short Span Steel Bridge Alliance, we're going to look at short length bridges. Now, the Short Span Steel Bridge Alliance deals with simple span bridges. I'm not going to limit it to simple span. I'm just going to say bridges that are less than or equal to 140 foot in length. And when I narrow that down, we can see that the average length and the average number of spans becomes much more consistent, which means this is going to be a more consistent comparison. And now what are our results? If we look under the PPVC or the capitalized costs, now steel rolled beams is the least expensive and the precast box spread is next. Now we do see, I do have that statement down here that all are similar with none way out of balance, but we do see that the steel plate girders are a little bit high, but that would be expected when we're talking about span ranges, you know, between 20 feet and 140 feet, because plate girders, you know, they're not as economical below about 80 feet, but still all are similar with none way out of balance. We can also look at the present value of future costs, where we can just kind of say, okay, what are our expected future costs in comparison to each other? And then average length, average number of spans, and that type of thing. Okay, so like I said, I talked to so many counties and states and consultants and that kind of thing. And the question is, which type of bridge is best? Is it the precast? Is it the rolled beam? Is it the precast I-beam, box adjacent, yeah, whatever. And here's where I come back and say that all are similar with none way out of balance. That if I take the overall weighted average capitalized cost, it comes out to be a little over $252 per square foot. All of the bridge types, the 5 different bridge types, all of their averages are within 14% of that. And now I didn't show it here, but I do in a longer version of my talk. If I look at the standard deviation range within each type, or I'll say coefficient of variation of 20 to 25%, and if we're within 14% of the weighted average, what that means statistically is that any one type of bridge may be most economical for a given bridge project. That there is no one type of bridge that clearly beats the others. And that brings me to my conclusions. One reason I do this and one reason I look at initial costs is because there is a preconception out there that concrete is less expensive than steel. And you thought I was going to come in here and say, hey, steel beats concrete, hands down, you should build everything out of steel. No, that's not what I'm saying. The results of this and what we've known for a long time is that typical concrete and steel bridges are competitive on initial costs future costs, life cycle costs, and bridge life, and that owners should consider both steel and concrete alternatives for individual bridge projects. And so that finishes me up. I believe I'm on time, more or less. There is my contact information, but I really encourage you to go to shortspansteelbridges.org. It's a great site that has lots of different stuff on it, including Acro case studies. And it also has these reports on the original life cycle cost report and the one I did not get to today, galvanizing. And with that, I am going to pass it back to Betul.
Thank you, Dr. Barker. This was very informative. I know that you've done, entire hour-long presentations on this before, and we've asked you to condense it all into only 15 minutes. But, despite the time constraints, I think I echo everyone's sentiments here when I say that you did a great job, and we appreciate you sharing your findings with us. So Dr. Barker concluded that owners should consider both steel and concrete alternatives for individual bridge projects. Now, this is very significant because there is a preconception that concrete is always cheaper than steel for short span bridges. Now, truth be told, there is a time and a place to use one or the other, and cost is not always the determining factor. I can't speak to all the benefits of concrete over steel. I'm sure there are many, but I am not an expert on concrete bridges. What I can speak to is some of the benefits of steel bridges as compared to concrete bridges. So steel bridges typically are lighter in weight. They can achieve longer spans and therefore can be cheaper if you can eliminate piers. They're easier to maintain and inspect. Everything's out in the open. Unlike with concrete, with the steel reinforcement being embedded, you don't always know what's going on. Rehabilitation to extend the lifespan. So say there's an impact on the bridge. Say there's a part that that needs to be modified or fixed or changed. With steel bridges, this is an option. You don't need to worry about taking down the whole bridge to rehabilitate it and extend the lifespan. And as I've mentioned before, you can also consider the future usage of bridges and being able to modify it from a single lane to a double lane. Steel bridges, particularly panel bridges, can give you that option. Also, benefit of steel versus concrete is significantly quicker installation times. And I'll get into some of this stuff in a bit of on some future slides. What I want to talk to you today is, when we talk about accelerated bridge construction, we're really talking about pre-engineered modular bridge systems. In this section, I'll be discussing some of the attributes of the Acro 700XS panel bridge system, and I will demonstrate how accelerated bridge construction can solve some of the common bridge infrastructure challenges that we had discussed. So panel bridge, the Acro 700XS system can reach clear spans of up to 91 meters for single lane, 76 meters for two lane, and an unlimited span or an unlimited length for a multi-span. We offer various different roadway widths ranging from 12 feet or 3.67 meters to 14.63 meter roadways. These are easily assembled and launched. They're fully galvanized, so there's no concern about corrosion or rusting over time. We have various different cantilever walkways available for one side, for both sides, to be able to allow pedestrians to utilize the bridge as well. And we have various deck options, including timber, epoxy aggregate, anti-skid surfacing, or plain steel decks for asphalt overlay. Here's the system. As I mentioned, it's a modular sort of thing. Panels are assembled, and the configuration of this bridge can be different depending on the criteria that we design for. So whether you have one line of trusses, whether you have or 3 lines of trusses per side, like this one here, we will determine based on the loading criteria what configuration needs to be designed for the bridge. The floor beam or the transom, what we call, also varies depending on the design criteria. We have various different widths. We have various different strengths of transom. And then we have the decks. So these are the steel decks, orthotropic steel decks. This is a curbed deck that basically on either end or either side of the bridge has a curb. And then we have just the standard decks. And essentially the width of our bridge is determined by this, I guess, by the width of this deck. So you can do it in increments of the width of this deck. The truss configurations, as I've mentioned, you can have various different configurations, anything from all these little symbols you see here, SS, DS, DD, almost sounds like coffee, but really these represent the truss configuration. So SS is a single. It's a single truss line with a single story. And then you have DS, double truss line, single story, et cetera, et cetera. So we have various different reinforcing cords as well. So the R that you see there, SSR, means, single story, single truss, reinforced. And so there's many iterations of, designs that we can come up with to meet the requirements of your design. In terms of guardrails, we do offer an integrated post and box beam guardrail steel that essentially takes the worry away from damaging the truss panels if there is an incident or if there's impact. The transom, so it's connected to the transom or the floor beam. Therefore, the impact is absorbed by the transom as opposed to, and you minimize damage to the truss itself. We also, oftentimes, tri-beam guardrails can also be used. These are standard. They're not supplied by us. They do not meet the crash tested criteria like the previous one does. With the two tubes, with the two box beams, this is crash test level compliant, up to AASHTO T at test level 4. And Canada does follow the AASHTO code as it relates to the guardrails, so it complies. Tri-beam, as I mentioned, they do not meet the crash tested criteria under AASHTO, but often they don't need to when they're used on rural roads and bridges. So the tri-beams can be applied directly to the truss beams, but and this is often the case for rural municipalities. We see municipalities and the MTO specifying a tri-beam or flex beam right on the panel trusses themselves. And this is an option. However, we highly recommend if you are going to go this route to sort of to ensure that there is a double truss line, bridge line, so that there is a level of redundancy, because the impact is absorbed by the truss and not by the transom in this case when you're using a tri-beam. So Acro, we determine the truss configurations based on the design criteria that we're given, be it the span, the roadway width, design loading, the design life, the code that's being used, etc. And we only design the bridge superstructure. So we don't get into the design of the foundations and such. We only design the superstructure and supply the superstructure. And we essentially give the loading at our the reactions at our bearings to the people who are designing the foundation so that they can use this information to design it. We also supply a bearing layout to sort of, I guess, to assist with the abutment designs in terms of the geometry. Now, in terms of installation, these systems, they're fairly simple to install. There's 3 typical methods that are used: cantilevered, crane assisted, and crane lift-in. I'm going to very briefly go over all of these. Cantilever launch method allows for an Acro bridge to be rolled into place without the use of a crane. There's a launching nose that we design. And essentially this is utilized when you don't have access to the opposite abutment to be able to use a crane to pull it. So you can only do it from the one side, and this launching nose allows you to be able to push it across to the other side and then remove it once it's there and once you've jacked it down onto the abutment. There's a short little video here that I'm going to show you about, let's see if this goes, yep, there we go, the cantilever installation method. So essentially this is just showing how these little parts assemble It's sort of an incremental assemble and push technique when you're doing a cantilever launch. So right here, they have assembled the launching nose and transoms and the beams. So this one is a double single. So you have the double truss line and you have a single story. So as they assemble, so they have the cords and they have the reinforcing cords that they're putting at the top and bottom, and then they begin the push. So you don't need necessarily heavy duty equipment for this. You can use a dozer, an excavator, anything. Like we provide rollers, as you can see on the ground there, that you would push. So they're incrementally assembling and pushing. That what you saw there at the back is just, it's actually the decks, the steel decks being used as counterweight, which is typically the case. And there you go, they've jacked it down and they're putting those steel decks into place after the fact. And at this point, you can install guardrails and such as well. So that was a cantilevered launch method. Typically, what most people use is the crane-assisted launch method. It's basically an Acro bridge can be launched using a crane if the required equipment is available and you have access to the opposite abutment. Let me just go back to that for a second here. So this is similar to the crane, to the cantilever launch in that there's rollers and you push it. However, there's no launching nose, so you push it up to a certain point, essentially keeping the center of gravity on the home abutment so it doesn't tip over. And at a certain point, close to the middle, the crane can take over and lift the bridge, and you can push and pull with the crane. And then finally, with the right size crane, an Acro bridge can be lifted into place. This is the fastest method suited for exceptionally demanding situations where timing and speed are critical, and assuming that the span is not enormous. This is a very efficient method of installation. You just rig it up onto your crane and you place it on your abutments. Now this here, this is an approximation, an Acro approximate speed of construction. So these panel bridges go up very, very quickly. This is by no means an exact sort of time estimate, but given our experience, a span of 10 meters can be assembled in a single day. And that's significantly faster than concrete type bridges. So next, I want to present some bridge application examples and demonstrate how accelerated bridge construction through the use of steel panel bridges can address the need for speed, durability, versatility, and cost effectiveness in project delivery. And I'm going to go over these fairly quickly. We do have a lot of slides and not a lot of time, so hopefully you'll sort of capture the gist of these examples. So vehicular bridges done with the system. These are pre-engineered. Length, width, and strength are easily customizable. These are conveniently transported, fast assembly installation, safe, reliable, and durable systems for vehicular bridges. So here's an example here in the Yukon. This is one of the first permanent bridges that we did. It has a sidewalk or a footwalk that we call on one side with a custom railing system. So this is in the extreme cold. Acro doesn't use notch tough steel, but this bridge has held up very well with no cold, brittle fracture. It's a 36-meter span bridge with 2 lanes with CL65 loading, highway loading. This bridge here, it's in Montreal. Contractor built foundations for a purpose-built bridge, but they ran into difficulties and essentially got kicked off the job. And we came in with this panel bridge and got it back on track. It's a single lane, 3.6 meter single lane bridge. Another permanent bridge example, this one, same as the previous one. You can see the bridge has a slight camber. It's a 99 meter span bridge, single lane. It's a 4-span bridge, 99 meters total length, and it was designed for CL65 loading. This bridge here, permanent bridge, Township of Lanark Highlands in Ontario. This one just showing the asphalted highway, or the asphalted surface, and also the TL4 guardrail, the integrated post and box beam guardrail. The township, put this out to tender, and it was over budget, and the township knew of us, and because we were doing a project nearby, and they considered our panel bridge, and ours was, nearly $1 million less than the original consultant designed bridge, so it was a nice solution for them. Here's another permanent bridge example, City of Port Hope in Ontario. Permanent bridge, asphalted, TL4 guardrails. This is our wider 2-lane bridge, 9.1 meters. Has custom railings at the ends, and it has a nice bike rail as well. This one, Edison Road Bridge in Vienna, Ontario. It was prefabricated with steel stringers and a steel grate decking as well, grid deck. Well, this allows mud and snow to fall through. Here's a project in Toronto, Ontario. This is I want to show you this because it has a poured in place polymer deck. Consists of a polymer modified cement that is applied at a thickness of 12 millimeters, and it seals the surface from salts and de-icing materials, petroleum, and most chemicals. So that's not something that we supply, but they were able to do this over top of our plain steel decks. Here's a bridge in northern Manitoba. This shows, timber decking. The main span is 76 meters, or 3 spans. There are 3 spans, but the main span is 76 meters. This is on a winter road in a very remote area. It has different configurations for the different spans. You can see, at the forefront there, it's a single story, and then in the middle there, it becomes a double story. This was designed for CL65, CL65 loading. This one here, it's a temporary service road bridge purchased by the city of Regina, and then it was repurposed for temporary secondary road bridge as a secondary road bridge. And I just wanted to show this because this is something that municipalities can do. They can take ownership of a bridge, purchase these panel bridge systems, and then reuse them as needed on future projects. Here's a project in Chicago. This is a cambered vehicular bridge, positively cambered. It was needed to provide enough clearance to clear the water. This bridge is also super elevated, and there's decorative pedestrian railing on this one. So 11 meters wide, 43 meters in span. This one here, another cambered vehicle bridge in the USA. Actually, this one crosses the Erie Canal. It was designed to be supported by existing piers. So no need to beef up the piers. They used what was there, and our bridge was light enough to be able to go on the existing abutments. Now, in talking about long span bridges, we have systems, suited to long clear spans of up to 100 meters. We could do multi-spans with no limit in length, single or multiple lane. These can be rapidly mobilized and installed, and they're designed for high fatigue permanent applications. So this system here, it is the Maybe Delta Bridge system. It is similar to the 700XS in that it's steel, it's modular, a little bit different. These are much larger in size. These panels are 4.5 meter modules, but we can do 4.2 meter to 10.5 meter roadways, really in increments of 1.05 meters, which is the width of the decks for this system. These are easily assembled and launched. You can achieve long clear spans. These are pre-cambered and preloaded connections fully galvanized as well, similar to the 700XS. Cantilever walkways are available with this one as well, and the anti-skid surfacing on the decks. So, you know, one of the features of this is that you don't need two truss lines or triple truss lines on this one. A single truss line can accommodate most of the bridge criteria, and it gives a more sort of open view as compared to having multiple truss lines. So this essentially is just a schematic showing you the various different components. You've got similar, you know, you've got the transoms, you've got reinforcing cores, you've got panels, you've got decking modules. So this is another example of a modular bridge system. Here's an example here. This is called the Caroni Bridge. Bridge linking north and south. This is in Trinidad and Tobago. It's a nice looking bridge, pretty hefty bridge. It's a span of 81 meters, and the installation time for this, 21 days. Here's another one. This is in Switzerland. It's replacing an old bridge with a new permanent structure. This is a 90-meter span bridge, and environment was protected in a single span. We need to put a pier in between. So, you know, we discussed previously about environmental regulations and such. I mean, this is not in Canada, but in Canada, you know, there's lots of regulations. So, you know, where you can avoid piers, it's definitely a plus to be able to do so with a system like this that can achieve long single spans. This is another long span bridge here. This was built for 35-ton trucks. It was built in 1983 in northern BC, but it stayed in place until it was meant to be, you know, a short-term temporary bridge, but it stayed in place until 2017. It was heavily overstressed and it was inspected regularly with no signs of damage. So this one was built on one side and pushed across. nearly 430 meters in 70.1 meter spans. This bridge here, this is in Chile. It's a 1.4 kilometer span, multi-span bridge, 2 lanes. I'll discuss this bridge again a little bit later in the emergency bridge section, but you know, it's a beautiful bridge. It was put up very, very quickly. Here it is in a different view. Just goes to show, you know, we certainly can do, you know, very long bridges with multi-span. Then on the opposite side of the spectrum, you know, we also can do very short span bridges, and we have done so. This one here, just a 12-meter bridge, 2-lane bridge designed to CL65 loading. This is Crosslink's Forest Hill Station in Toronto, and the bridge was used to maintain traffic while construction of the subway was underway. Another similar such project, Vancouver. You know, you build the bridge, you trench it, you build the subway, you bury it, then you remove the bridge. It makes it very simple for use in these applications. Bridges, you know, I'm not going to get into all of these details, but you know, this is something that we do also offer for short span applications. It's another system that's conducive to accelerated bridge construction. Here's a couple of drawings or photos showing examples. This is a 14-meter, 5.5 meter wide beam bridge. It's a low profile, as you can see, 15 inches from underside of bearing to top of deck, and it's very, very quick to install. Excuse me, another example here. So these come in basically 6-foot wide segments. Very easy to transport, very easy to install. Now moving along to pedestrian bridges. So these panel bridges can be used for pedestrian bridges as well. They're quick and easy to install. They're supplied with your choice of timber or epoxy aggregate anti-skid deck. They do have the hot dip galvanized coating as well with minimal maintenance requirements. And they can be designed with a positive camber for aesthetics. Here's an example of a pedestrian bridge. This is the Chidok pedestrian bridge in Hamilton. This is a 79-meter single-span bridge, a pedestrian bridge, 2.4 meter wide. It was the only option for this particular project as a system. You know, it's modular, and they would not have otherwise been able to bring steel girders they would have had to build a road because the site is 1 kilometer walk into the site. So they were able to do this because of the modular nature of this panel bridge system, the Acro panel bridge system, and they pushed the bridge essentially with a dozer. So they wanted this to be a pedestrian bridge, but also to accommodate pickup trucks. So so it was designed to accommodate vehicles as well. Here's another permanent bridge. This one, West Penn Rail Trail in Pennsylvania. Ideal application for modular bridges due to limited site access in remote locations. So multi-span, but it was a nice looking bridge, nice project. Here's an example in Quebec. The span 36 meters, 3.6 meter wide, and this is a timber deck with timber rails. Essentially, you don't need anything fancy necessarily for pedestrian bridges in this application. And we also do snowmobile or recreation and rec bridges as well, similar to this one. Here's another example. This one's in Nova Scotia. And here's a sort of an alternate application. This is a pedestrian bridge. It's a temporary pedestrian support bridge. So they needed to support a timber truss bridge. They were rehabilitating that. And we had just done a project like this in the US. We gave them drawings. Dead load of wood bridge was distributed to our bridge. Then they could jack our bridge up and thus jack the wood bridge up in order to be able to replace the damaged parts. So they didn't really, use this as a pedestrian bridge to go crossing over it, but it was a nice solution to I guess, rehabilitate the existing covered bridge. So we also do offer box type pedestrian bridges. Essentially, it's got our Acro 700XS panels on 3 sides. And this is a nice temporary solution for, during construction and whatnot as a pedestrian box bridge. And then we get into sort of the heavier loading. So we have done a lot of railroads bridges in the past, ideal for this, engineered to accommodate both freight and passenger trains, designed to support ARIMA loadings, and available for rapid deployment, can be installed in just days. And it's suitable for both permanent and temporary railway applications. I'm just going to show you a couple of these very quickly. So this is the CP Railway in London, Ontario. It used Cooper E80 design load. That's a very demanding code. And really, this is just to attest to the fact that, if the railway has confidence in our capabilities, then you should have confidence in our bridges, under highway loading conditions. This is the same bridge here. Here's another one in the US and Ohio. And this one's in Brooklyn, New York. And then tour rentals. I mean, really, when one of panel bridges, I think a lot of times this is what comes to mind. Temporary detour bridges. I've just shown you a bunch of other applications and permanent applications that can be that the system could be used for. But this definitely, these bridges are well suited for temporary and detour bridges. It can certainly achieve accelerated bridge construction, economic rental solutions, safe detours around construction sites. So let me just show you a bunch of photos here. So this one is a project in Quebec, 3-lane bridge. It's a 60-meter span. It was 11 meters wide. It's cambered and has an asphalt surface, and it has a full drainage system, this one, and it's super elevated. So it's got multiple things going for it here. This was a very interesting project. Here's another one. This is sort of, it's the widest bridge we have ever built. It's Autoroute 40 west of Montreal. Worst road, considered the worst road in all of Canada for traffic. 3 lanes plus the shoulders for this one. And there was an asphalt deck. Another temporary bridge here, Turcotte Interchange in Montreal. Large clear span, cambered. It's over a railway, has an asphalt roadway. This one was installed as a full cantilevered launch The whole structure was built on one side and cantilevered across with a launching nose. Here's another example, 3 lanes wide. Speaks to our capabilities, 3 lanes of fast, furious highway or freeway loading. This one here in North Vancouver in BC, it was a really tight spot for installation. It was launched on rollers onto a temporary pier and pushed out a little further, and the crane receded on the other side. This is in Quebec, one of 2 detour bridges, very difficult installation, tight spot, but there's the other one, the second. And then moving right along just to a different application here, shoring. So this is something, super prop shoring systems for a wide range of vertical, horizontal, and knee bracing applications. This is not, I'm not going to get into this too much because, in the interest of time here, but really this is something that we can provide as a support scheme, tower, shores, assembled essentially using our panels from the bridges as the shoring components. We also movable bridges. Here's an example here in West Palm Beach, Florida, of we supply the towers, the gantries, the crosshead, everything really, the hydraulics and mechanics for this bridge. And bascule bridges, we could do that as well. This one's in Martha's Vineyard. We provided the approaches and the bascule, full package, including the mechanical parts and the hydraulics and everything. In terms of heavy haul, rugged solutions, definitely to support heavy off-road vehicles, machinery, and equipment. Here's an example here. This was an interesting solution. 15 rows of trusses. This is in Labrador, Boise's Bay. This was done because the truck has a heavier axle than the capabilities of our standard bridge. So it was an innovative solution to this challenge. Just again, showing industrial heavy haul examples of heavy haul bridges. And then in terms of kits and utilities, there's solutions to that with innovative solutions to support supply and extraction. Here's some examples. This is in the city of Cambridge. There's a water treatment plant. There's a utility pipe that was laid over this. Here's another example. It was a 43-meter span and it was designed for pipe loading. Here's an example as well. This pipe was hung on hangers on the outside of the bridge. Now, in terms of these emergency bridges, I mentioned previously, rapid response teams to deliver restored infrastructure. We've done many different emergency bridges, and I'm just going to go over just a few of these. Here's one. Acro provided two-lane bridges within a week, just to sort of highlight the timeline in which, if there's an emergency, we have the inventory in stock, how quickly we can mobilize and replace situations and make it safe again to travel over. This was the World Trade Center after 9/11. The towers and ramp were supplied for this. It was in for several years. This one has an epoxy deck over the ramp, and they were hauling 100-pound beams at times over this. It was designed for highway loads. This is that bridge that I showed you previously under the long span bridges. So this is the bridge in Chile, the emergency bridge in Chile. There was an 8.8 magnitude earthquake. 2 cities were cut off because the existing bridge was damaged. And this bridge was installed in 88 days. So 1.4 kilometers of bridge was installed in 88 days. Here's another example in New Orleans after Hurricane Katrina. This was sort of the most aggressive bridge project at the time for Acro. This was 2008, and we supplied this in 3 months. So here's an example. It's not, these bridges are not necessarily limited to international emergencies. Right at home, sometimes we have, small emergencies, and something like a sinkhole or something can be rectified or remediated with a panel bridge system very quickly and efficiently. Here are some other additional examples. And there are a whole bunch of other applications that I'm not really even going to get into that can be, that a panel bridge can accommodate. Lots of capabilities with the modular system, such as this. So I'm just going to quickly jump over these other applications. I know we're running out of time. Ramps, roll-on, roll-off ramps, and such. So I mean, we talked about various different applications that can be utilized, or that can be, I guess, served with this panel bridge system, the A700XS. The features and benefits, these are made from high quality, high strength steel, versatile applications, permanent, temporary, and emergency use. Very easily customizable, according to the desired length and width that you need, or the strength that you need. They're pre-engineered, prefabricated to save you time and money. They're precision engineered and designed for safety and durability. They're all hot dip galvanized for weathering and minimize maintenance. These are fast and easy to assemble and install with a light crane or a bulldozer. These are installed with support from a team of experienced site technicians. Full service design and engineering, according to the CHBDC code. Unlimited total spans, as we had discussed, and really shipped to anywhere in Canada. So if nothing else, I mean, what I'd like for you to take away from this presentation today is the recommendation of Dr. Barker. Owners should consider both steel and concrete alternatives for individual bridge projects. I've shown you the Acro 700XS panel bridge system, a proven advanced modular steel technology, and how it can solve various bridge design challenges. These are expertly manufactured using high quality, high strength steel, easily customizable, precision engineered, hot dip galvanized, as we had discussed, and really rapid installation, which was really the name of this presentation, accelerated bridge construction. Hopefully I've adequately demonstrated how modular steel solutions can help deliver a project more quickly and safely and efficiently. I thank you very much for your time today. And if you have any questions, hopefully you would have had them answered in the comment section via Gordon. If not, you can always reach out to myself. My contact information is here. Again, I thank you for your time.
All right, thank you. It appears the clock is our enemy today, as the hour and some additional time has flown by. I want to thank both of our speakers for taking the time today to share their knowledge and insight on accelerated bridge construction. Once again, the webinar has been recorded and will be made available on OGRA's website and also our YouTube page for you to go back and review the information a second time. Also, the slides, as asked a couple times in the Q&A pod, will be circulated or shared within the coming weeks. Now, my last duty as host is to wish everyone a safe and healthy rest of the day. Take care. Thanks for joining us.